Okay, so on worksheet 7.2a, problem number 4, what does it tell us? I don't know because I lost my sheet. I sat it somewhere dumb. I'm glad I'm recording this. Here it is. Okay. Okay, so it says a car is on a circular track with a radius of 100 meters. A, the car goes from 0 to 60 miles an hour in 6 seconds. So let's start by kind of writing some of this stuff down and seeing if we need to convert anything. All right, so here's what we know. We know that the radius of the track is 100 meters. Okay, I kind of cheated here. Later on, we're going to worry about the radius of the wheels. So that's why I wrote track. I'm sort of just, I know what's going to happen farther down the line here. All right, it's going from 0 to 60 miles an hour. So what's the 0, you guys? Initial, I just gave away the answer, velocity, right? All right, and then our final velocity is 60 miles per hour, right? Right away. Oh, that's not in meters, radians, and seconds, so I should convert, right? Is it okay if I just tell you what it is, and then if you're one of the people that needs help with the dimensional analysis, we'll do that later? Is that cool? So if you convert this, it gives you 26.8 meters per second. And if you don't know how I did that, or how to do that, I guess I should say, then grab me, okay? All right, and it tells us that this takes 6 seconds. And question A wants to know the angular acceleration as it goes around the track. So that's our given information. Are we all good with that? What is this little... Oh, I see. Okay, so step 1, meters, radians, and seconds. Check. Step 2, write out givens. I kind of did that as I did step 1. Step 3, decide angular or linear. All right, so here's the deal. This is a perfect example. Look, we're looking for angular acceleration, right? But we're not given any angular information. So what I'm going to do is I'm going to work in terms of my linear values. What thing do you think I should try to find? The linear acceleration, right? Because all of my values here are linear. Let's find the linear acceleration, and then what? Then use a jumper to find the angular. Follow? All right, the alternative is this. Use jumpers to convert these velocities to angular, and then find the angular acceleration. But I think in this case, it's easier to just use the jumper once at the end instead of converting both of these to angular. Follow? So, acceleration is Vf minus Vi over t. So let's see, our Vf is 26.8. Our Vi is 0, our time is 6. So divide this out, and you get what's 2.8 is going to be 4.3 repeating meters per second squared. Is that right? Something like that. Okay. So that represents the acceleration of the car as it's speeding up going around the track, right? So, right? Faster and faster. Good? Now, because it's going in a circle, there's also angular acceleration. The rate at which it's sweeping out an angle as it goes around the track is getting bigger and bigger. So, I can use this jumper equation. If A is alpha r, then alpha is A over r. So, the acceleration of the car is 4.43 meters a second squared, and it's driving around a track with a radius of 100 meters. So divide that, and you get 0.0443 radians per second squared. Good? Any problems with that? Okay. I just broke rule number 4. I found my solution, but I didn't label it. So let's go over here. I just found my alpha. Let's write it down. That's 0.0443 radians per second squared. That way, if I need this number anywhere else, I'll have it. Cool? Does that make sense? All right, part B. If the wheels have a radius of 35 centimeters, find the angular acceleration of the wheels. Ooh. So, wheels. So the problem tells us, for part B, it tells us that the radius of the wheels is 35 centimeters. Convert. That's 0.35 meters, right? It's 100 centimeters in a meter. All right, so here's the gazillion-dollar question. Don't shout it out. Stop and think. Which, if any, of these numbers that deal with the car going around the track, which of those numbers also pertain to the wheels as they rotate on the car? Don't shout it out. I want everybody to think. This coffee mug is ridiculous. All right. Thoughts? What do we got? All right, sure. We got Tim.
Time stays. Time.
Oh, yeah, okay. So when you say the time, so what would that time represent?
It still represents the amount of time that the car is moving. If the car is moving, the wheels are turning. So it's a time frame of...
Yeah, that makes sense. Okay, so I agree. I think we can still use this time. Oh, shoot. I neglected to carry a number over. Darn it. Okay, well, we'll come back to it. We'll find it in a minute. Okay, so the time is 6 seconds. All right. What else? You got an idea, Abby?
Your linear acceleration that you calculated can be used because it's like the outer edge of the wheel, so you can still use that.
Yeah. Okay. So here's the deal, you guys. Anytime you've got a thing that's rolling, remember I showed you this? If I roll this piece of tape, if I roll this roll of tape, then in the time it takes for the tape to make one complete cycle, the distance it rolls is equal to the circumference, right? So the distance traveled by the tape is the same as the distance traveled by a point on the outside edge of the tire, right? Anytime something is rolling, the linear values of a point on the rolling thing are the same as the linear values of the thing that's moving. That was a bad sentence, but do you know what I mean? Okay, so in English, our car starts with an initial velocity of 0. That means that a point on the outside edge of the tires starts with an initial velocity of 0. Then, as the car speeds up to 26 meters a second, that means a point on the outside edge of the tires is also going at 26 meters a second. So all of the linear values travel over, which means that the VI is 0, the VF is 26.8 meters a second, and the acceleration that I found on that other page that was 4.43 meters per second squared transfers over. How about the angular value? What does this angular value represent, you guys? That we found in part A. What is this? Here's my car. I'm going to keep doing this till somebody tells me what it is. Well, I know that's a bad idea because nobody will ever tell me. All right, so it's going around in a circle, right? So this is the acceleration angularly of the car's motion, right? Good? What's it asking us for in part B? Not the angular acceleration of the car, but the angular acceleration of the wheels. Do you guys agree? The wheels are spinning way faster than the car, like in terms of like frequency, right? In terms of how many cycles it completes, right? So you just use a jumper equation again. The only difference is the wheels have a smaller radius, right? So instead of being this acceleration over 100, it's this acceleration over our radius of 0.35 meters. And it gives you, what is it, 12 point something? 13 point something? What is it? 12.74, thank you. I missed if it was 12 or 13. Cool? All right, so that was B. And then finally, part C. How many times will the tire rotate in the 6 seconds? What is it really asking you for? When I ask you how many times it'll rotate for, how many times it will rotate, I'm asking you angular displacement, right? So for part C, here's what I know. I know my angular acceleration is 12.74 radians per second squared. I know my time is 6 seconds. I know my initial angular velocity 0. We're trying to find our change in theta. Does that make sense, you guys? I cheated a little bit. Everybody cool with why the initial angular velocity was 0? We knew the initial linear was 0, right? So that means the wheels weren't rotating, right? Okay. So, is there an equation that uses these guys? So I'll be honest, all those angular equations, I do not have them memorized. I do have the linear ones memorized though. So in my head I'm going, oh, well this is delta x, this is v, this is t, this is a. Oh, 1/2 at squared. Oh, delta theta is 1/2, not a, but alpha t squared plus, instead of vi, it's got to be omega I times t. And then plug in your numbers and you're done. Oh, no, you're not done. So if you do that, let's figure out what it gives you. 12.74 times 0.5 times 36 plus 0. So that gives you 229 watts. Radians, right? Because this was in radians. So this is radians. So to find the number of rotations, now we convert. 2 pi radians is 1 rotation. And so that'll give you your answer. So divided by 2 pi. So you get 36.5 rotations. Cool? Questions, concerns, issues, anything? Everybody good? All right, cool. So that's cool. That hits a lot of bases. So let me